Nobody else dressed up? Man. That's all right. So, we're in the midst of charges and whatnot. Do you have any questions about anything? Turn it over to you for a moment. Things that we've discussed, you've read, you've noticed, homework, anything. Yes? You don't understand the why. So have you looked at my explanation yet? Well, that would help. Not as a be condescending, but just to remind everybody that on the homework, if you don't understand why it's the right answer, go back and look at the key. That's why I put it there. So the question was, if you're standing on a bathroom scale and it reads your weight, if all of a sudden the atmosphere just disappeared, you could remove all the air. Was that it? What does the scale read? Does it change? Increase or decrease? Yes? That's the key. The air is a fluid, and even though we take it for granted, we're displacing a certain amount of air in the atmosphere. And the weight of that air that we displace is the buoyant force. Thus, we're being buoyed up ever so slightly by the air around us. It's more conspicuous when you jump in a swimming pool, right? Because the water, you can feel that buoyant force because water is more dense than air. But there is still a buoyant force in the air. So if you get rid of the air, you get rid of the buoyant force it provides, and thus the scale has to support you slightly more than it did before. And you can, if you have a sensitive enough scale, you can detect that. Yes?
My first thought was that there is air pushing down.
Yeah, air pushing down.
So if it's here, it would decrease because the weight of the air was gone. So
okay.
would that
Okay, that means you're thinking it through. And I like when people do this with your superheroes too. You're thinking, oh yes, okay, the buoyant force is gone, but yeah, think it through. That part, it confuses people. I just forgot the term I use for it. Viability of your superpower. Think of some of the consequences that happen. You know, if you did this is cool, and this is how it could work, physics. But that also means, which would mean, this is one of those. If you got rid of the air, well then yeah, there's no air pushing down on the scale. There's no weight on the scale. Maybe the scale should read less. And that gets you thinking. The reason it doesn't is because the scale is calibrated. The air's on the inside and the outside of it. It's atmospheric pressure on both sides, so it's equal. So when you get rid of both, it's still the same difference. So if you just had the spring scale there, or your bathroom scale, and you just removed the air, it wouldn't change. But if you're now standing on it, it would increase. Thank you. Anything else? I give you these homeworks too. I chose which ones to give you on homework versus which ones I ask you on clickers versus which ones I get put on the test. They all kind of come from the same pool, that in my head. And this will be good for homework, while you have time to think about it. So if you don't understand those, that's a tip-off that you're probably not ready for the exam, which is in a week. Oh yeah. We'll finish this fluid stuff with current this week. We'll review Friday. And the next exam will be next Monday. Do you have?
Yeah, on the homework, the question where you're standing on a scale and the atmosphere disappears.
Yes.
So I didn't quite understand why I put that you'd weigh less, or you weighed less, because I thought the atmosphere was pushing down on you too.
Okay. I don't mean to be condescending at all, but that was the last 5 minutes. We just discussed that. Did you just get here?
No.
Oh. So short answer is I explained it in the answer key. So go there if what I'm about to say isn't enough. And the slightly longer version is you get rid of the air, you remove the buoyant force. So the air isn't helping support you. You'll be pushing down a little more. The scale has to support you slightly more. Anything else? Megan, I watched the video and your hair was just great again. I just from the pantograph. Thank you for doing that. Some people's hair is just kind of meh, but yours was great. All right. Start going back through the homeworks now, because when we get to review on Friday, ask more of these type of questions. Solidify your understanding. We'll go through that. All right. A little summary of where we're at. We got Coulomb's law, the force between charges. It depends on both charges. It's an interaction pair. And the distance they are apart, inverse square law. If you triple one of those charges, both charges feel 3 times the force, because it's based on both of them. It's, again, like mass. Just because something's more massive, the force between them in a collision is still the same. They'll be accelerated differently. That's the electric field. You put a charge in an electric field, and it'll feel a force on it. We use positive test charges. They will go in the direction of the electric field. They'll go with it. Electrons, which are negative, would go the other way. That's how they would naturally want to go. Electric field is that force per charge. So if you triple the charges, you've tripled the force, but you also tripled the charge. So just because you put a bigger charge in an electric field doesn't change the electric field. It changes the force on it, but not the electric field. That's just rearranged, kind of. I used to. When I started out, I would remember this one more than this one because it looked more like Newton's second law. A mass, the particle, but we're interested in charge this time, is being accelerated by the electric field. Now I have to admit, I remember this one more because that's how I conceptually visualize what an electric field is. It's a force per charge. Let's draw a few electric fields. How do they go away from a positive charge? Away or towards? Who's not sure? Be honest. All right, so you take your positive test charge, put it near it. What would it do? It'd repel. Right, so it goes that way. This will do the same thing. They want to go away here and here, but what's going to happen in there? It's like you got two coming at each other. Are these two going to repel each other? Yeah, Coulomb's force. Positive charge, same force, and they're repelling. So they actually look something like this. They come in and they repel each other. Or one here might go like this. And this one will start coming, but it's probably better pictures in your book. But you can kind of visualize that. Let's do positive and negative. It'll go from the positive, we just said that, so you now know it'll go towards the negative, so it actually goes straight across right there. This side will go away. This side, it's coming in. Away, away. This one starts heading away, but it's influenced by this one that wants to go in. So it actually curves on over. This one actually might, it's out there. So that you can see some of these electric field lines. They help you visualize easily the electric field, what's going on around things. So you can see right here, what would the electric field be right there? What's your gut tell you? 0. That's right. There's no field lines there. It's like the electric field from this is canceled by the electric field from that. Right. I bet you can guess something else. How do you think the electric field compares Oh, right here in this region compared to this region. What's your gut tell you? Yeah, it's stronger here. Electric field lines help us visualize that easily too. Here, the field lines are closer together. Here, see how far apart they are? So indeed, the electric field is less at this spot than it is here. So likewise, the electric field's strong right around a charge. The electric field lines are closer together. It's closer to the charge too. The distance is part of that. Out here, where you're farther away, you can see the field lines have spread out. So the electric field is decreased. Look, electric field is force per charge. Here's the force. So it's that per one of those Q's. It's still based on distance. So it should decrease with distance. In here, though, they're all spread apart. They don't even come together. Right there in the middle, perfectly symmetric. Yeah, it'd be 0. If you had 2 plates of charge like this, can you start to visualize what the field lines might look like around those plates? Same game, it's just like we stuck a bunch of charges next to each other and made a wall of charge. Which way do they go from plus charges? Away. So we know this. They start out at least like this, and here. And negatives? Towards. And indeed, look, you got electric field lines that just go straight across inside. Out here, though, it's kind of like, woo. It starts to head out and might bend around a few times like that. But out here, so the field's really strong in between there. You can store energy in that field here because the electric field's really strong there. It's actually a parallel plate capacitor. You put charges on 2 plates, put them near each other, create an electric field. Yeah.
So magnets, they work through electricity?
Magnets have a north and south pole, and you can visualize magnetic field lines. You've probably done that with iron filings or compass needles, and they go from north to south. They make closed loops. So you could draw them similarly, like around a bar magnet. Charges that move create a magnetic field. And if you have a magnetic field that's changing, increasing or decreasing, not just existing, but changing, that actually creates an electric field and can make charges move. That's the connection between electricity and magnetism. But we're not there. But yeah. So you could visualize some electric field lines with lightning. Let's see. You got a cloud up here, the ground, nice tall building, maybe a smaller house. You get the idea. Let's say, which way did I draw it? In the clouds, charges separate. And it can vary, but typically the top is more positive, the bottom's more negative. What's that do to the charges in the ground? Polarize them. Which charges are going to be attracted? Up towards the cloud. Yeah, so we're going to get positive charges at the tops and negatives down there, so to speak, to help us visualize it. So we've induced a charge. The ground's polarized underneath the cloud. And if there's a big enough difference in charge, the electric field grows as you add more and more charge. Can you see it? Electric field goes from positives to negatives. Wants to go away. Oh, sees the cloud. One here, it goes away, and you might actually have one to the ground. But you get the idea. Woo! All those electric field lines. Can you see they're closer together up here at the tip? So what do you think is going to get struck by lightning first? That's right. The taller, right there. It'll break down the air around there, make it more conductive, and that's probably where the lightning will happen first. It doesn't have to fall, it can go anywhere at once, but it's easier there, and it's more likely. Yeah? Yes, the closer the charges are together, the greater the electric field. When they're, and that's not always true. For a given voltage, which we haven't discussed yet, I'm getting almost right to it. They do, but yes. Distance matters with electric field. Force per charge, and the distance is in there, so yes. Distance does affect things, at least can. So we talked about energy. Work. We learned before it's force times distance, so if you take this force, QE, and multiply it by the distance, you have the electric potential energy change because you did work on it, or it did work. You can increase by this much or decrease by this much. Do you think it would take energy to push a proton and an electron together? Yes, no, maybe so. Who thinks yes? Who thinks no? It's a tie. The rest of you don't know, don't care. What do they naturally want to do? Proton and an electron, Coulomb's law, they want to attract. They're going to do that regardless. So it doesn't take energy. They'll actually give up energy as they come together. The work they do on each other. They're exerting forces on each other, and if they do that over a certain distance, force times distance, then they did work and the energy changed. The electric potential energy changed by that much. They'll decrease that amount because they want to go that way. It's like going downhill. If you got a ball up here and I let go of it, it wants to fall. What happens to its gravitational potential energy? It decreases because gravity did work on it. Here the electric field's doing work on it. How about two protons? Would it take work to push them together? Yeah, you can see that because they are trying to fight it. They want to repel. So it would take energy to put them together. How much? Force times distance. The force times the distance you try to move them apart. So that's the idea with energy. So if you have a battery or a power supply like this, what do? They have chemical energy. If it's a battery or it's connected to your power plant, power, energy, the rate we use energy. They do the work for us of separating the charges. These want to come together, so what's it do? It essentially is doing work to pull them apart. And you can store them on the two plates. That's called a capacitor. Here's two plates. Basically, a capacitor is just an insulator sandwich. The foam is an insulator. It doesn't let electricity flow across it. And here's the two conductors. So if you hook that up to a power supply, it uses energy and does work to separate charges, and it puts plus on one side and negative on the other. So thinking question, what do you think the overall charge of the whole capacitor is? That's right. Very good. It's neutral. It still has plus and minus. It's like it polarized the capacitor. It separated them, and now there's an electric field in here. You can picture it. And that stores that energy. The energy the power supply or the battery did in separating the charges is now stored right here. Each of those charges has a certain amount of energy. We have a term for that. And you've heard it before. It's very familiar, but that's all it means, really. Voltage. That is the same thing as electric potential. Just to confuse you between electric potential and electric potential energy. They are not the same thing. Electric potential is not the same thing as electric potential energy. Electric potential is voltage, and that is the electric potential energy per charge. That's our new one. So, who knows how many volts come out of the wall socket? Nope, not 12. Yeah, that's about 110. So that's depends on where you're at, but it's usually 120 here in the United States. 120 volts, we say. That's the electric potential. What does that mean? 120 volts. That means it has 120 joules of energy per coulomb of charge. Think of all the little individual charges, and they all have a certain amount of energy. 120 volts worth. That's how much energy the power company gives each coulomb of charge, so that we can plug in something and use that energy. They separated the charges for us. We use it up. A generator would create and do the work to separate more charges. So that's what voltage is. If you have a 9-volt battery, that's 9 joules of energy per coulomb of charge. Yeah. Yes. Yes, yes. Usually when somebody just says, what's its potential in the terms of electricity, or what's its potential difference? They should qualify that and explain what they mean more precisely. But what they're usually referring to, yes, is a difference in voltage, a difference in electric potential. So a potential difference is when this changes. We say, by the way, this is 120 volts. Relative to what? Remember, energy, potential energy is relative to what? What's the gravitational potential energy of this capacitor? Well, relative to what? Relative to the table, it's 0. Relative to the floor, it's something. So it's the same with electric potential energy. It's that energy relative to this distance relative to what? Or this energy relative to what? 120 volts is relative to ground, 0 volts. But you could have a wire that's at 100 volts, 100 electric potential, and another one that's 120 above it at 220. The difference is 120. So the electric potential difference is 120. If you plug it in, it'd work the same way, because the difference is 120 volts. You might have other issues, but voltage is always a difference. It's always relative to something, because it's energy per charge, and the potential energy is always with reference to something. So, you know the high voltage wires that carry like 100,000 volts? You see those signs, danger, high voltage? Could you grab one of those?
Yeah.
How come?
It's only one of the charges.
It's one. How would you grab it?
One hand.
And what else? Grab it with one hand? Yeah, I wouldn't be touching the ground, because that ends at 0. So now you just made a difference of 100,000 volts across you. You just set up a big electric field. What are the charges in that electric field going to do? Start moving. They'll be accelerated and you'll die. That's current. Current is the flow of charge. I'll write that one down. Current, it's given by I, and that's the change in the charge over time. That's coulombs per second, which is called an amp, after ampere. You've probably heard of, oh, that's 10 amps. That's the unit measurement for current. And that tells you how much charge is flowing by. So many coulombs per second. Current is just the flow of charge. So I'll probably fall susceptible to this, but it's a misnomer. When people say, oh yeah, the current is flowing in the circuit. Well, it's not a misnomer, it's just redundant. Current is flowing. Current doesn't flow, technically. Charge does, and current is the flow of charge. But whatever. Who like seen The Little Rascals, the new version? It's one of my favorite lines in there. Both Darla and I are singing a duet together. How redundant. Alfalfas. Thank you. But anyway. So yeah, saying current flows is a little redundant, but that's all right. So what gets the charges to move in the first place? I bet you know. They're just sitting there happy in the wire, in you, in this wire. What gets them to move? A difference in voltage, a difference in electric potential, a difference in charge buildup on the two sides. The electric field, all of those are correct answers. If I put you as a charge in an electric field, you'd accelerate. What creates the electric field? Separation of charges. That means each of those charges has a certain amount of energy. What's energy per charge? You now know. Energy per charge is? Voltage. That's right. So to help you with these circuits, as we start to flow circuits around, charge around, there's a lot of advantages. There's some disadvantages, but there's a lot of advantages to thinking of charge flowing in a circuit as water flowing through pipes. How would you get water to start flowing? Apply pressure. What would you physically use to do that? A pump. So I often think of power supplies and batteries as pumps. It's what pushes the water around. The voltage, the difference in electric potential is what pushes the charge around. Because it wouldn't unless you had a difference. If you're at 120 volts and 120 volts, they're at the same potential. The charges here have the same energy as they do here. Why do they want to go that way? They won't. It's just like if you have pressure, 120 pascals and 120 pascals. No fluid will flow. Fluid doesn't flow unless you have a difference in pressure. Charge won't flow unless you have a difference in potential. It won't start flowing unless you had a difference. Does that make sense? But voltage isn't what kills people. That's just what gets the charge moving. It's the charge that flows through you, the current, that could kill people. So you have to keep that low to be safe. Let's charge up a capacitor. Looks like this, microscopically internally. There's just a lot more area and they're closer together. So here's a big bad capacitor I have. I'm going to charge it up, connect it to this power supply, put it up to 3,500 volts. 3,500 volts, 3,500 joules per coulomb. Turn it on. It's now supplying those charges with that energy, and it's separating them. It's building up charge positive on one side, the same amount of negative on the other, because the whole thing's overall neutral. We're just separating. It's doing work. All right, let's see if that's long enough. Turn it off, disconnect it from the power supply, and now it'll just hold that charge in the hold that energy in the electric field unless I short it out. It's like connecting from one side to the other. I give it a path. The positives want to go to the negatives and vice versa. So that's what I'm going to do. You ready? Got somebody. Let's do it again. Charge it up. And it's work. It takes a bit. So I'll wait a few seconds. Separate more and more charges. The capacitor voltage is increasing because we're separating more and more charge. The difference in electric potential between the two plates across the capacitor, between those two electrodes, is building. Turn it back off, disconnect, and it'll hold that charge. So you have to be careful with capacitors. If you accidentally touch one that's charged but you didn't know it, that could happen to you. You ready? Woo! It's a doozy. I'm not touching that. That has a lot of energy. I could hurt myself big time with that. So I won't. You don't discharge it across yourself. Let's do another one. Oh, yeah.
The wire, or like what is going through like the wire? Is it positive and negative?
What's going through the wires? You can have charges flow that are positive or negative, but it's usually not the protons. But you could have positive ions that are flowing. Most often in normal conductors, it's the electrons that are free to move around, and it's the electrons that flow. And remember, they go opposite direction of the established electric field. So the electrons are flowing one way in the circuit. We say the current, by historical convention, flows the other way, the same direction as the electric field, to be consistent with our positive test charges. But that they are moving. Yes?
So because batteries store chemical energy, like you said earlier, would it be considered a chemical reaction you discharging the battery like that?
Oh, yeah. So batteries, yeah, they do store it chemically. It's like there's two different materials in there, and they have the positives and negatives, and they want to come together. So they set up, if you hook something up to the battery, it makes the charges in the circuit want to go to one side or the other. So it's not really a chemical reaction that gets them to move. It's the electric field. However, that uses up the material inside a battery physically. That's why batteries go bad and die. If you use up those materials, they don't already have the difference in charges to have that influence in your circuit. A capacitor doesn't have those charges. It's already separated. So you can't just hook something up to a capacitor and run something. You need something to separate them in the first place. Then you use it up. Then you have to do it again. Rechargeable batteries are somewhere in between. Where's my... Let's do this one then. Here's two capacitors. And they're connected. I'm going to connect them to the batteries. So the capacitor is being charged like that. This just isn't as scary. All right, I'm going to put the switch in the middle. Now the capacitors aren't connected to anything. They just hold the charge. Now let's connect them to this light bulb. And you can see it uses up the energy. Where'd the energy go? Yeah, light and heat. So we can do it again. And each time we use up the material in the batteries, and eventually they'll stop working, and I'll have to put in new batteries. All right? Charge is held in the capacitor. I'm ready to use it. And it discharges. Now it supplies the energy to the light bulb and uses it up. Now the voltage on the capacitors is 0. It has no energy per charge because we just used it all up. I want to charge this capacitor up. This is a water bottle. I just put water inside years ago, so it's dirty by now. But it's a capacitor. Here's aluminum foil on the outside, one conductor. The water on the inside, second conductor, separated by the insulating plastic. See, it's an insulator sandwich. It's a capacitor. So I ought to be able to hook this up to a power supply and separate charges. Connect that to the top. Turn it on. I'm connected to ground. The other side. Okay. This, yep, has charge all right. So if I touch both at the same time, I'd give it a path, and the charge would flow through me. Actually, I already have the charges. As soon as I touch it, I would see the difference in electric potential, the difference in voltage. The electric field would be established once I touch it. And all the charges in me, the electrical path, would start being accelerated. We're going to make a circuit. Who wants to do it? Come on down. We could get half the class. Come on. The more actually, the better. Come on down and form a big oval. Let's learn about circuits. If you have a heart condition, just stay in your seat. I'm not worried, but why chance things? Form a big oval and hold pinkies with your neighbor. We're going to make a circuit. Come on. We need more. Some from this side. I've done calculations. I don't intend to kill people. Well, I get some good observations about current in a circuit by doing this too. Anybody else? All right. So here it is. I need somebody to be the switch. Who would like to be the switch? Any takers?
No. I'll be the switch.
All right. I'm going to get in here then. One thing. We want this charge to flow in our circuit through us. So if you're touching the table, step away, because some of it could leak that way, right? If it has a path. And we want it won't flow right now because we're not touching. If any of you let go, the electric field can't see both sides, and nothing will happen. So nobody can let go. All right, when you're ready, you touch the top screw. Because that'll touch the water inside. See, I'm on the outside. It wants to get from the outside to the inside. But I'm going to force it to get the path to go through us. He'll be on the inside, I'll be on the outside.
Just with my hand or just with like my finger?
Whatever. Thank you. Thank you. Good observation.
It went that fast?
Yes. That's one of my major points of doing this. Well, okay, the main one is it's fun and shocking people. But physics reasons why. Yeah, she noticed that everybody kind of jumped or yelled at the same time. Here's a myth. Here's a myth. A lot of people think when you flip a switch, you turn on the lights. Although these have a delay of 3 seconds. But anyway, you hit the switch. People think, oh, as soon as you flip the switch, the current starts flowing and goes around really fast back to the power supply. Wrong. You know, you don't pay the power company for charge. That's not why they bill you. You already have the charges, right? They're already in us. They're already in the wire. They're already in your Xbox. You pay for the push, the power. As soon as you flip the switch, the electric field is established at the speed of light nearly. And so all the charges are now in that electric field. They start marching in time. So all the charges in you and me all felt the electric field at the same time and started moving. So we all felt the same thing and at the same time. Don't think a charge is going whizzing around the circuit and super fast. That's wrong. There's a question. Not anymore. So let's look at the charge. If there's an electric field that way and I'm a positive charge, what am I going to do? I'm a positive charge now in an electric field. We flip the switch. Which way will I move? Let's say I'm a positive test charge in an electric field directed that way. Electric field, here's some field lines to help us visualize the electric field. If you put a positive test charge right here, which way will it go? That way. So if now I'm saying the electric field's that way, and I'm a positive test charge, which way will I go? That way. I'll be accelerated that way. So picture charges. They are moving fast because they have a temperature. So they're moving around. They're like going fast. But they bump into everything else and just kind of... But now they're in this electric field that's trying to move them that way. So what do? But then they bump into something and kind of come back. Over time, this is kind of what they look like. The charges in a circuit do move, but at a snail's pace. They're barely moving along. It's called a drift velocity. So yeah, picturing current in a circuit as charges, totally wrong. The charge is already there. They just start drifting in the direction of the electric field. Yes?
So if I would continue to have my hand on the screw and like everyone were to continue to leave these, would we have felt the charge for like a continuous amount of time?
Yes, while you were connected, the electric field would be established until we use up all the charge in the that was separated on the capacitors. So at some point, nothing else would flow because you used it all up. And those discharge a lot quicker. So we used all of it up. I checked afterwards, so I didn't accidentally touch it and shock me with what the remaining part of it. I went like this, and it didn't do anything. If I heard a little spark, then there would have been some left. But my second observation. Usually the people don't want to be the switch because they think it's going to hurt more. But just 'cause we all felt the same thing. You flip the switch, we're all in the electric field, we all have the charges, they all started moving at the same rate. We all felt the same thing. We would actually say in our circuit, which was a series circuit, all connected one after another, there's only one path for the current. A series circuit, the current is the same everywhere in a series circuit. So the current through Jordan was the same as the current through you and me. Parallel circuits, it can split. You have multiple paths to go along. Here's a few real examples of some other capacitors. Here's a really big one. They kind of look like stuff like this. You've probably seen them in circuits if you've ever looked. You know what, if you take one of these apart, you know what it is? It's just an insulator sandwich. You could even make one. Foil, conductor. Wax paper, insulator. More foil. Wax, foil, wax, foil, wax, foil. That way they can get a lot of area, roll them up, put them close to each other, and you can increase the capacitance this way. And then they seal it up, and there you go. You have an insulator, a whole lot of insulator sandwiches rolled up. That's the way most of these capacitors are made. It's just an insulator sandwich. Here's one that just changes the spacing between the two plates. It's variable. It's essentially like doing this. The area between the plates, you're just changing it. So it'll hold a different amount of charge if you adjust that. You can shield from electric fields. Radio waves, cell phone waves are electromagnetic waves. Electromagnetic. They have a changing electric field. An antenna picks up that electric field. If an electric field goes past this conductive antenna, what will the charges in there want to do? Stay put? No, they want to move. They'll be accelerated when that electric field goes by. That goes into your radio and tells them, oh, okay, now I get the signal. I'll make sound. Let's turn it on. Whoops, wrong button. So I'm picking up a radio station that broadcasts at a certain frequency, but it has an electric field. Here's a conductive metal mesh cage. So the frequency of this radio can get through the holes to the antenna of that station. Let's try a different station.
What's the deal with emails anyway?
We'll try this. Gets through that one.
Related to Hillary Clinton's private. They don't need to hang their head on anything. And then going forward, I have no, I really believe we can go out there and we can win all these three remaining games and put ourselves in a great position.
I won't lie, I'm confused. It usually blocks more than by now.
They were in the same position a year ago. Arizona.
That's a better station anyway. Let's see. Different size waves, and it does matter. What it's doing is the electric field is influencing the charges in the cage. They were before also. But if the waves got through, we heard the station. This one we don't hear. Now this whole thing is charged because the electric field came by and it's moving the charges around. But what it's also doing is the electric field everywhere inside the cage is canceled out. Think about it. If you got some charge on this side, say it's positive, then there's negative on the inside. Well, that negative makes an electric field inside. But the opposite thing's happening over here. And the two fields cancel each other out, kind of like this. And it works out that everywhere inside a metal conductor, the electric field is 0. For this station, it is. It's called a Faraday cage. And how many of you have ever lost cell phone reception when you go in a tunnel or an elevator or whatever? Same thing. 50% of the time, I can't get phone calls back here. That's where my office is, behind there, because I'm in the basement underneath all this metal. And so it blocks the electric fields from allowing the charges in my phone to move appropriately. Sometimes it works, sometimes it doesn't. It gets through. All right. Let me just look real fast before I send you away. We got that. Got that. Good, good, good. We got voltage. Remember, it's what makes the charges start moving. Once they move, we now have a current, the flow of charge. We will continue next time with Ohm's law and see how resistance in a circuit helps influence how much those charges move or don't move, how much the current will be in the circuit. And then we'll play with series and parallel circuits so you can see how hooking things up differently can also change stuff. Any questions? Yes?
When you change the radio, what does it?
Great question. When I change the station, I'm actually varying, it depends on how they set it up, a resistor or a capacitor. Usually it's a capacitor. You're doing something like this. And we haven't got to resistance, but as you change how much this charge this can hold, it changes what frequency the charges move back and forth. And if you want the frequency that they move back and forth to match up with the frequency that they're being broadcast at. It's called resonance, just like in music. If you're trying to push somebody in a swing at the wrong timing, it doesn't work. Same with this. It's just with charges moving back and forth. So you have to match up. And so you're adjusting the circuit by changing the capacitor or a resistor to match that frequency. Thanks, everybody. Happy Halloween.